Review problem number 11. We've got a ballistic collision again. This time we fire a bullet into a block. They have a perfectly inelastic collision. They stick together. That combined bullet plus block object rises up to a final height h above where it started from. And our task is to figure out the initial speed of the bullet. So this is a process that happens in two stages, and we need to use two different physics concepts to analyze it. The first stage is this collision where the bullet gets embedded in the block. That is a perfectly inelastic collision. We'll use conservation of momentum. Once that collision has taken place, this bullet block system rises up to some final height. During that process, energy is conserved. So we can use conservation of energy for that second part, and ultimately we'll be able to express the bullet's speed in terms of our given quantities, the two masses and the height that this thing rises to. Because if you were doing this as an experiment to measure the bullet's speed, the thing that you would be observing is the height that the system rises to. That's the easily measured quantity. Measuring the speed of the bullet is harder, so we infer the bullet's speed by measuring this easier to measure quantity, h. Okay, so let's do those two steps. I'll start with conservation of momentum. We have the bullet's initial momentum, and we have the block's initial momentum, which is 0 because it's stationary. And that equals the final momentum of the block plus bullet combination immediately after the collision. So I'm using this symbol V to refer to the speed of the bullet block system right after the collision happens, when it's still at the level of this table. So I'll do one little step of algebra. And we see that we can relate the bullet speed to this speed right after the collision, but we still have two unknowns. We don't know this value yet, we don't know that value yet. So I need to do my second equation, the conservation of energy equation for the second part of this process. And then I'll have enough equations to solve for my unknown. So we can use conservation of energy immediately after the collision, as this block is rising into the air. So the initial scenario here is immediately after the collision, when that block is at table level. The final scenario is when it reaches the maximum height. So we might as well define zero potential energy at the level of the table. This block bullet system has an initial kinetic energy of 1/2 mv squared, where we're using this same v value that refers to the speed of the system immediately after that collision. That equals the final potential energy, m g h, plus the final kinetic energy, but since this is moving vertically at the highest height, its speed is 0. So 0 kinetic energy at the end. And we can do a tiny bit of algebra and find that that speed is root 2gh. And now there's just one more thing to do. We substitute this result in to our earlier expression for the speed of the bullet. And now we have a formula that lets us calculate the speed of the bullet based on a single measurement of the height of this system after the collision. So this problem is an example of a situation where we need to use several different techniques to analyze it. We had to use energy and momentum. So I might ask you to explain why we needed 2 techniques, explain why each technique applies to a particular part of the problem. We had to use conservation of momentum for the collision because it was a perfectly inelastic collision, which means energy is not conserved during that collision process. So we got to use momentum for that collision part. Then after the collision, as the object rises into the air, that's a very standard conservation of energy type problem that we've done a lot of examples of. So energy is the right choice to analyze that second part. And that gives us 2 equations where we can solve for our 2 unknowns, and we combine those 2 equations for an expression for the speed of the bullet.